Okay, question number 4. The diagram shows a rigid wire AB pivoted at the point A so that it is free to move in a vertical plane. So it will be pivoted at here. Okay, sorry, I'll call a pen. So it will be pivoted at here. So this is where it will be. Sorry, it will be pivoted at here. Okay. Now, the lower end of the wire dips into mercury. A uniform magnetic field of 6.0 times 10 negative T acts on into the paper throughout the diagram. So into the paper. So this is a magnetic field into the paper. Now, when the current is switched on, the wire continuously move up out of the mercury and then fall back again. Explain these motions. So B, the force on the wires due to current may be taken to act at the midpoint of the wire. So when the current first switch on, the moment of this force about A is 2 times 5 times 10 negative 5 Newton meter. Calculate A, the force acting on the wire, and 2, the current into the wire. Okay, so now let us solve A first. Okay, so the A is required to find when the current is switched on, the wires continuously move up and down. So it means that the wire move up and then moving down again. So why does this happen? Okay, why does this happen? So first thing that you have to say that is actually the current is at right angle to magnetic field. Okay, why? Now let's go back to the diagram. You see, this is the current going from here. Now this is the magnetic field that's going into the paper. Okay, you can see going to the paper. So means that each is right angle to each other. So when it is right angle into each other, means that according to left hand rules, okay, there is a force. On A, B towards the right. Okay, towards the right. So wire leave mercury and breaks. Okay, sorry, and breaks contact. Okay, then current stop. Okay, so if when current stop means that AB will force back. So AB falls back and make contact again. Okay, so this process will keep on going and going and going until your battery dies out. Okay, now for part B wants you to find the force. Okay, the force of the let's go back. The force acting on the wire. Okay, the force acting on the wire. So what do they give you? They give you a moment. They kind of wait here. Now you are in electromagnetism, but they give you a moment. So what can we do from the moment? Okay, so let me draw a simple diagram again. So this is what they pivot here, and then this is the rigid rods, and they are in the mercury. So we make one assumption here is, okay, moment the given here is 3.5 times 10 power negative 5 Newton meter. Okay, now we make an assumption that the moment is act on the center over here. Okay, so means that I have the force over here so that it can be pulled up. Now this is at the center of the rods, so means we choose half of it. Okay, so moment will be equal to F times R, 3.5 times 10 to the power negative 5. Okay, now what is your R? Your R will be half of the distance. Okay, given here is 7 cm, so 7 cm and half of it will become divided by 2, so it's 3.5 times 10 to the power negative 5. So my force that I have here is actually 1.0 times 10 to the power negative 3 Newton. Okay, so this is part 1. Now part 2 wants you to find what is the current. So I know the force means I will know the current, okay? Because in electromagnetism, BIL equal to F, okay? So your B will be, the given here is 6.0 times 10 power negative 3 Tesla, negative 3 Tesla. So where I is what you have to find now, the L here, okay? So the L here is actually the whole. It's no more half of it, it's whole. So this is my L, okay? Which is the current going through the conductor, the length, the current going through the conductor, which is the whole things, which is 7 and 10 power negative 2 equal to F, which is this, okay? So my I finally will be 2.38 ampere.